Hey, okay, we should be live. How's it going, everybody? So we are in Logic World today, and well, I was up really late last night because I got stuck in a wormhole of like math, I guess I should say. So Red Command in my Discord server has been telling me for a while now that you can actually have a application-specific integrated circuit that just does like squaring, you know, like where it's like multiplication but both inputs are the same. But, you know, why would you build a multiplier and have two inputs where you then have to tie them together if you can build a circuit that only has one input and does squaring? So to actually do that, we need to build a 2 by 2 multiplier. So two bits in, 4 bits out. So that's what we're going to do, and I started messing around, and I was going to keep going, and then I realized I should actually go live and do this. So that's when I actually set up my thumbnail and stuff for this. So what we're going to try to do right now is build a 2-bit Wallace tree multiplier. It's going to be better than a ripple multiplier, or like a an array multiplier thing. But yeah, so what we're going to use is we're going to get some AND gates out here. And I tried doing this with relays, but they're too tall, so I'm not going to do it with relays. Also, I'm just now realizing that that will be an issue. What am I doing? Okay, so the goal here that I need to have is let's build a vertical. I don't know if I like this word colors. I might change it, but we need a vertical line like this just so we can be off the ground so that we can see underneath the circuit when we do that. I forgot even how to delete something as a B. Jeez, grab. Oh, let's zoom in. T used to be delete, but it's not T anymore because that's going to be talk. So Jimmy said he rebounded it, but I don't have a menu for the rebinds. It's X, Z, Control Z, no undo. It's not that. That opens up console. That's weird. Backspace? Delete. Delete just deletes the thing you're holding in your hand. Yeah, I'm not sure what that could be. Okay, also, is there anybody actually watching this? Cool, we got one viewer watching this. Hello. Yeah, so let's try. I guess we'll... I want that to be at the top. Hey, how's it going? I do not know how to pronounce your name in Russian because I'm an American and I cannot speak Russian. But I'm glad you are here with us. Thank you for joining. Hey, what up, Nano? Not really sure what I'm doing with these inputs right now. Also, Nano, do you know how to delete things in the beta? He rebound the key off of T, and I don't remember what it is. Chelover Razumni. Is it like Shelover? Or like Che or She? Also, you guys can hear me, right? I'm not too quiet, because I know I had to like amplify myself a lot on R D R. Thank you. All right, now I figured it out. It's R. It's literally the button right next to T. Okay, cool. I'm an idiot. Okay, so we have 2 inputs done. Now we need the other 2. What is my field of view set for? How do I even change that? This field of view feels a little close still, but alright. So if I turn on that and turn on that, alright, cool. So I turn them all on. Cool, okay. Alright, boys. So here's our 1s, 2s, and 4s. So now we're going to have a 2-bit adder here. And that 2-bit adder is going to have a carryout. So we're going to have 3 bits here plus the 0th bit. That'll get us 4 bits, and that is our 4-bit multiplier. Or 2-bit input to 4-bit output. So yeah, I guess I need to build a 2-bit adder now. And yeah, that's really stupid simple. I don't know if those need to be 3 high. Actually, yeah, they do. Because then we need to grab XOR gates. Alright, so here's going to be our 2-bit adder. Actually, I'm going to remove. Oh, that's so nice. I'm so glad that's a thing. Actually, no. Yeah, I'm gonna work on all this. Is gonna be like optimized Mandelbrot hardware, so that reduced area and reduced operations, especially if I'm doing things with relays. I want to reduce the amount of operations I have to use relays for, because those will slow down the game as well. Like, they give a speed up and a slowdown, so I want to balance it. Like, I want to use them where I can, and obviously not use them where I don't need to use them. Alright, so now I should be able to test this out. Nice, okay. Each one goes one spot. I keep pressing T to remove stuff. Alright, so now I need the relay. the last XOR. Oh, that's definitely a lot smoother than it used to be. So we're going to say carry in gets XOR'd with propagate. And now if we want the carryout to be the same delay, we need to put a 1-tick delayer. I know these delayers are still fucked with how Jimmy made them work, but I think the 1-tick one will work for what I need here. So now I have my carryout. Now it goes through 1 tick like the XOR does. So now that should be synced, so I should have carry in. Nice. And now the carry-ins will never really be used on these things, but now that I have this module, we can, I don't know which one's the bit base. I can just control G. Okay, so now we need to grab fucking prime. Fucking prime. Whoa, what did I do here? So, oh, I changed the color. What button did I press to do that? P? I forgot what menu that is. Man, it's been a long time since I played this game. It's been a long time since we got a new beta release. That's why I'm playing it. Alright. And now this input comes in here. The bottom one stays, not used. And now this is 1, 2 ticks. So if we want the we want to sync this. This is going to be 1, and that's going to be 1. Carry logic is no delay. We have 1, 2, 3, 4 bits. There's our 4-bit output. So now let's see what happens if we do 2 times 3. Do we get 12? No, we get 2 times 3 is 6. Yeah, okay. 3 times 3 is 9. Okay. Alright, so here's our 2-bit multiplier. So now what do I need to do? Well, I need to pull up my resources. Okay, so we have a 2x2 Vedic multiplier, which is basically wait, they're using a different 2x2. So you get a sum and carry out. Oh, because you only have to use half adders because They will never be carry-ins. Except for that half adder that has... let's try it that way instead. So we'll do we'll copy that AND gate and input, and we'll take off the here. So we'll do Control G, and then we added this right here. So G R. All right. So now we have our input array here. So now A0 B0 is this first one, which comes through and does nothing. Now we're going to take B0 times A1, so let's turn that one on. B0, alright, we'll do it like this. B0 times A1, you want to take that one, and we want to take then B1 times A0. So now we want B1 times A0, which would be that one. So now we want these two. And we want to use a half adder on those two, so we need a should we do it like this? There's our half adder. And then the topmost bit gets a half adder. Okay, so now we need to delay this bit here by the delay of that half adder. So we need 1 tick of delay added to P0. So let's do that right here. Pretty cool being able to look at papers and just build what's like inside of it. Alright, so there's the 1 tick for that. And now we need to do the 1 tick for the topmost bit as well. So now we will do... Okay, so now all of our signals are synced. Now we'll throw the second half adder that we need on P3 and P2. So now we're going to say... I'm going to bring this down like so. Do that. Now there's going to be a tick of delay there, which means we need a tick of delay here, and that means we need a tick of delay here. Off of that. Off of that. Let me go ahead and turn off this. Okay, and then now what we're going to do is we're going to use the same matrix or the same half adder. We're going to do it there. So now we're going to have we'll throw our AND gate down there. We'll do it like this. This one's going to be a bit tricky, but we'll do something like that. And we'll use this side here and that side there, like that. I want to, Z, is that no clip? I forgot the no clip binding. Oh wait, you just type in no clip, that's right. There we go, okay. So this input is coming to there, which then gets... I think I can do that better. I think I can just take that one there and that one there. Okay. So now out of the half adder, we have... Okay, cool. So now here are our bits arranged. One, two, three. Actually, let's do it like this. let's put them like this. It's the carryout, and then that, and then that. Okay, there's our 2-bit Vedic mult. And we built it according to this diagram right there. Yeah, sorry, Nano. I mean, you saw it though, so. So let's try 1 by 2. We got 2. Now let's do like 2 by 3, and we get 6. And 3 by 3, we get 9. Okay, so same thing. Now we're completely synced. And now there's no carry stage, Nano. I don't know if anybody. Okay, so I just realized there's no carry stage here in the math. So, oh my god, that's fucking beautiful. So you can pipeline this thing at 1 tick. Each stage is 1 tick of delay. 1 tick of delay for the AND, 1 tick of delay for the half adder, and 1 tick of delay for the next half adder. So I can fit 3 numbers in 3 ticks. That's insane. Okay, another reason to use this Vedic mult over like a standard multiplier. It literally doubles your throughput like that. That's insane. Okay. Okay. See, boys, we're going somewhere now. We just doubled our throughput by changing it from this design here to that design. This design, this is 2 ticks, but this stage here is it's like 0 ticks. So you can't really pipeline this. Yeah. So you can't. You need to pipeline this as 2 ticks, not as 1 going through that, 1 going through that, because it's instant going through there, so it'll screw up. Here, there's no carry on the adder because we're just using half adders. So yeah. Okay. So now we need to build. Now that we have the 2-bit Vedic multiplier, now we just need the 2-bit square, which is, you know, really, really easy. So now we're going to build, well, I guess I'll just I guess everything I build, I'm going to control G off this so I get the same height, and then we'll just delete everything off the stick that we don't need. Alright, so now what we need to do is we need 2-bit input. Why does that not... Oh, because it's... What the fuck did I do here, man? So if I just add one more like that... Alright. That should be the same height. Yeah, that looks like the same height. Is that over there? Yeah, it is. Okay. Alright, so now we're going to have our 2-bit input. And we need A0. I'm just going to rotate these. How do you rotate these? Okay. So we're going to say there's A0 and then P0, then P1 is just like float, like it's just a blank placeholder, it's just like nothing. Three and 4. Then bit. So now we need to AND the two bits together. I have a feeling I'm going to be able to redo all this much smaller in a second. So now we AND the 2 bits together. Actually, fuck that. We're going to do this here. Okay, so we're going to AND them. So now we use a half adder, which is just an XOR and an AND gate, and the two inputs to the half adder is the most significant bit and then the output of that. So we're going to say oh, and you can click F to switch that. That's nice. Excuse me. So we say one set of inputs comes from that. The other set of inputs will come from... Fuck, we need to sync it. So if that's going through one tick of delay there, before it goes into that, we need to sync it with a tick of delay like this. And then out of there can come like that. And we'll put it like that. Okay, so now it's one tick into that from both. So now we need 2 ticks of delay on this. It's just the least significant bit. Obviously it doesn't matter if that's always going to be 0, it doesn't matter how many, there's no input to that, it's just there as a placeholder. So and then bit 3, or P2, is the sum, and P3 is in. So if you look here, now this is a squaring circuit, so now if I put in 1, 1 squared is 1. If I put in 2, 2 squared is 4. If I put in 3, 3 squared is 9. Okay, so now we have 2-bit square and 2-bit mult. Alright boys, we're going somewhere. Anybody in chat a little confused about what's going on? Have any questions? Yes, it's me ripping a bong right now. It's Sunday. We're building some circuits. We're smoking some weed. We're having a good time. Just trying to pass the time, boys. Till well, I don't know till, but yeah. I am going to go brew up some coffee. So if anybody's in chat, just give me like 2 minutes. I'm gonna go brew up. Well, actually, give me like a few seconds. I gotta go press the button on the machine. I'll be back, and then I'll go grab it this time. All right. I'm gonna have to grab that in a few minutes. Yeah, so in the meantime, I guess we'll just look at this paper, have this up. So, now that we've created our 2-bit squaring circuit, and we've created our 2-bit multiplier, now all we're gonna need are those basic circuits and adders, and from there we're gonna scale up. And this is done recursively. So that when you build one, you're gonna use 4 of the previous modules that you built one of, to then build the next module with then a few adders stuck on there. Then you're going to take that new module with make 4 of them, so 4 copies, and then a few more adders, and now you have double the bit width. In doing this, you're massively parallelizing it while making each stage 1 tick pipelineable. Whereas if we did it before, each stage is 2 tick pipelineable. So, yeah. Just grinding a little bit of weed up, my boys, my family, my streamer fam. Sounds like we need to get some more Sevish going as well. So let's pull up this. Oh, no, they're playing. Okay. Just gotta turn up the volume. Yeah, if anybody doesn't know, Sevish is a band that makes microtonal music. So instead of like classic, like 20 or 12 tone equal temperament that we use, they mess around with their sounds. Okay, so we need to build this right here. And this looks like a little sloppy to see, so we're going to actually pull it up in digital here. File. We need to open up in digital. Is this it? Oh, this is the Vedic multiplier. If you were to use the 2-bit multipliers we just built as these basic building blocks, then this is a 4-bit version of it. Alright, so anyway, let's open a recent. Let's open up 4-bit square. There we go, that's what we have here. So we can see here's our 2-bit squares. So if I run this, and we put in like the number, say 3, well, we already know that works because on our 2-bit ones we can put in the number 3. Well, if I put in the number 6, 6 times 6 is 36. Oh. Oh, something fucked up there. I thought I fixed this last night. Did I not fix this last night? What the hell? How is that getting a 9 on it? How is that getting an 8? Oh. Oh. Okay, yeah, because I had to redo that circuit, so all these got... Okay, wait. So yeah, this is an easy fix. So we're transitioning from Logic World to digital real quick. Sorry, boys. But this is like my simulation tool that I use for stuff. God damn it. So clunky doing stuff like that. Wait, what did I just... Oh, I'm so dumb. Wait, why did I do that? This is... Okay, yeah, this is 1-to-1. It's the bottom one that needs to be changed. Okay. So, P0... So P3 is really the 0th bit up here. P2. No. That's wrong. P3 would be the most significant bit up there. P2 would be the least significant bit up there. P1 would be the most significant bit here, which if we follow comes up to there. And the least significant bit would then be this guy here. Alright, sorry about that. I had to rebuild those last night. Alright, so now if we put in... We get 24, which that's 36, and the 6 times 6 is 36. Written in binary is the same as having, 1 0 0 1 0 0. And we can pull that up on our calculator here. We type in hex 24 decimal 36. Alright. So if I put in like the number 15, we better get E1. We do. That's 225. Okay. So I'm gonna go grab that coffee. Yeah, Red. I'm designing well, this is the circuit laid out in digital, and now I'm gonna that's the circuit laid out in digital. Now I have the 2-bit squaring circuit here, and the 2-bit Vedic multiplier here. So now that I have the 2 basic building blocks of this design, I am then able to, because then I need that Vedic multiplier here, and I need the 2-bit squaring circuits here, and then I just need 2 adders, and then I just need to shift some bits around, and then recombine some buses, and that's it. So it's going to be relatively cheap here to build like a circuit that's specific to do squaring. But now I'm going to go grab that coffee because it's done brewing. Be right back. Alright. I'm back. So now, let's do it, guys. So we're going to need a 4-bit input. And we're going to okay, let's see how we're going to arrange this. So that's the multiplier that's going to be smack in the middle. Our 4-bit input. So we're going to need 2, let's make a board over here. Hey Red, do you remember the command to change the fuck? Oh, there we go. It's X. All right, he changed it. So let's. I like going with like vibrant colors, which I guess is like that. So I might as well use that. Okay. Cool. Is that because I turned off ambient nuclear? I don't know if that helps me. Oh, that's what gives it the dark edge. Oh. Alright, whatever. Alright, so, I'm gonna Control G. Grab a copy of this tall boy. Stick him right on here, about like that. And then now I need the 2-bit squared. So the multiplier gets the bottom 2 bits and the top 2 bits of the number as A and B. That's interesting. Okay, yeah, that's right. And then my squares get the other 2 bits. So let's arrange the input numbers off of a 4-bit input. Alright, so we're gonna remove these because I know how to hook that back up. Remove that, remove that. That means we can remove that. That software is called Digital. I mention it a lot. It's a free to use software that I actually use at work. It's actually really cool. Is if I go to analysis, if I stop the simulation here, if I go to simulation speed test. Oh, that's right. That only really works in sequence. So if you have like a clock in your circuit and you do that speed test, it'll tell you the maximum rate at which it can like simulate it. And if you have a good computer, it's like over megahertz speed. Logism, you get like kilohertz speed. So this software is basically, well, orders of magnitude faster than Logism. and it also allows for things like exporting to VHDL, where if I wanted to 4-bit square test, because I already have a 4-bit square.vhdl, so if I export that, yada yada yada, like if I labeled all the pin names, it would export there. Because, like, I just have to label that pin as like an output pin and give it like a name, and I would have to do that for my. And once I did that, well, actually, I think I can do that right now. Out file export VHDL. There we go. I exported. So now I have a VHDL file that describes this, and I can export onto my my either a CPLD or an FPGA or like whatever, or like I don't think you could put this on a PLA. This is too advanced for a PLA. But you could, that's what I'm saying. You could, like, this software is super advanced, and it allows you to do some really cool things, like actually use it in real life. So I'm working my way towards eventually having Mandelbrot, but I need like 133 million units, I think, to do the Mandelbrot the way I wanted to do it. So I think I need to re-evaluate. And that's why I'm just doing it in Logic World first. And so the goal here is to have a 16-bit squaring unit and a 16-bit multiplier by the time we're done, using the Vedic method, which should hopefully save in size of the total thing. And the less relays and stuff in the total size of it, the more we can have in the world. That's the goal, because the more parallelization we can get out of this thing, the better. So we're going to need a lot of them. So I can add, oh, and I should probably give you the, because you can't just Google digital unless you have it in your history like that. There we go. That's the link. Just download the latest GitHub, and you'll be prime. Let's use through-hole pegs. I think those work. Oh, we also got sockets, so we can work with stacking and stuff now. So if we need to do that, we can, which is nice. I don't think this design is going to require a lot of it, because it's going to be a lot of just like bussing by hand, it feels like. Bus it down, Tatiana. Alright, let's see if that worked. Just hook up I love being able to just do that, like resizing boards like that. That was so hard in Tongue. I'm sure everybody knows. Also this. Dude, brilliant. Brilliant, Jimmy Bravo. Okay, so what the fuck? Okay, that makes sense. 1 times nothing isn't gonna do anything. Let's see, that one goes there. That's what I wanted. So it should go. And then that's row. So bottom row, top row, first column, second column. Okay. Cool. So bottom row, bottom one. Yeah, so that's 1 times 1. So now I could do 1 times 2, 2 times 1, 2 times 2, which is 4, and then 3 times 3, obviously. Okay, so, alright, so that's how I'm going to arrange my inputs, like that. Now I'm going to need to probably, excuse me, make this board a little bigger. And then we're going to grab this. I don't know why it rotates like that the moment we grab it. Jimmy, if you're watching, I don't know why it does that. Maybe you do. Okay. There's the multiplier hooked up. Now we need the squaring circuits. Did I even hook up that multiplier right? The bottom 2 bits go into the bottom bit of B and the top bit of B, and then the top 2 bits, the bottom one goes to the bottom bit of A. So yeah, we just split it up into 2. Bottom one goes to the bottom one. Yeah, okay, that's fine. Okay, and if it's not, we'll just work on it later. So the output now is 4 bits. Now we want to right shift it, so basically we're just going to inject a 0. So if we want to left shift it. So basically what we're going to do is right here. This is our left shift. Now you see it doubled. So this is 1s, and that'll always be tied. It will always be 0. So then, well, that's obviously 2. So everything doubles just by injecting a 1 that's off. So like just like that, or a 0 that's off like that. So now we have a 5-bit number that comes out. Cool. Now we're going to take the 2 bits that go horizontal. Alright, so now we on the multiplier we have them going diagonal, or we have them going across. So we will have now, I'm going to grab a copy of this, Control G. And then, so we're going to take okay, so I'm going to have to replace this. This. I'm glad those pegs use 0 ticks. Okay. And so that connects, and then now I got to get rid of that. Actually, no, I don't even need that. I can just go do like that. Okay, there's our 2 inputs to the square, the 2-bit square that produces a 4-bit result. So now we're going to take the bottom 2 bits. The bottom 2 bits of the number, which go to the bottom 2 bits of it. So we're going to say this one and this one. And then we can, oh, what sucks about this design is Control G. Oh, hell yeah, I got it like that. So, okay, cool, so I can just, we'll add like 2 in height. Grab that, stick it on. Like that. And then all we need to do is then, stick the AND gate on it. So the AND gate output. Oh, okay, yeah, it's the half adder. So then we need to take a delay here. Tie that like that. Grab that, pass that to there. Now, the least significant, what? Let me check the original one. The least significant bit goes there. Alright, and then so we have the most significant bit and the AND gate that have to go in. Okay. So we have the most significant bit here. And this. Does that work? I don't know. Let's try it. Before we just like accept that it works without knowing, and this could be the thing that fucks us. Alright, so... Huh. Not right, for sure. Wait, what? Oh, I think... Oh, that is. 2 squared is 4. Okay. 1 squared is 1. 2 squared is 4. 3 squared is 9. Okay, no, I'm retarded. It is correct. We are good. Uh-oh. I guess you can't delete and toggle at the same time by accident. Anyway, these work. So now it gets this bit comes there, and that bit comes there, like that. So now basically we have the low here and the high here. So we're going to take the low 4 bits. We're going to take the low 4 bits, and of them we're going to take the low 2 bits and take them off. And that's of the square. So we're going to take the low 2 bits here. I don't know how big this has to be, but we're just going to like branch them off. Okay, we have the low 2 bits. Now we need to bring... Now we're going to need a 4-bit adder. So I'm going to go to that 2-bit adder that we built over here. Oops. Control G. Press R on that. We're going to press R on that and that, and then we're going to Control G. R, and then we're going to Control G. Perfect. I forgot how to pick block. And then we need a 1-tick short delayer. Pop that baby right there. Cool. So now we have 4-bit adder with a 1-bit carryout that's synced with the sum. So now we'll Control G that board. Excuse me. Okay. Alright, so we took the bottom 2 bits out. Now the top 2 bits here go into the bottom 2 bits of one input of the adder. So I guess we'll stack this adder, or can I rotate that? So ideally I'd like to be able to oh, I know what I'd have to do. Okay. Alright, so Control G. I think I just need to do something like this. Control G. There we go. I want that rotated the other way. Yeah, like that. Fuck it. Yes, and that becomes a new parent board. Okay, cool. Cool. Okay. So now I have my vertical adder. And now you can clearly see your 2 inputs. So now to make this a little bit easier, Control G. Fucking prime. Okay, so now we're gonna call this side here. This input here is going to be B. So I'm going to put a label. I like how you don't even have to click in the box to search for an item. It's already clicked in, so you can just start typing. Nice. What's the X? Yeah. And we want it to be B. Okay, so the B input, the least significant 2 bits are the most significant 2 bits of the 2-bit square of the small side. So this would be input B 0, and this would be B 1 like that. And we'll leave the top 2 blank like that, says there. Now the A inputs, oh fuck, that's supposed to be a 5-bit adder. Well, look what we've got to do, boys. Oh, and girls, if you're watching. I don't think girls are interested in this shit. Motherfucker. Relay. So what's up, chat? Still following along? So we need to and there. Delete that to replace the XOR. Gotta flip it like that. I like how that's a feature. Instead of using a delayer, we'll use the XOR as the delay. Okay, so now we just need to Control G. Nice. And then that goes to there, this comes here. So now we say take that with that. So it gets it, the one in front of it gets its, oh, I should probably hook up the carry properly. So you get the carryout of the previous one plus the sum of your last. The carryout of your previous one plus the sum of your last. The sum of yours, sorry. Carryout of the previous one here is wrong. What the hell? Carryout of previous one, sum of current. 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 Oh, maybe it is right. Oh, that's right. And then the carryout of the previous one. Oh, yeah, I am right. Okay, yeah, jeez. And that's exactly what it said. And then this will always be 0, and that's my final result. Okay, cool. I don't know why I did that. I should be at the bottom. Oh, I just fucked myself some more, didn't I? Carry out a previous sum of current. Carry out a previous sum of current. Carry out a previous. Okay, so now there we go. Oh my goodness, why am I so dumb? And watch, I'm gonna screw with myself again right here. Carry out a previous one, sum of current. No, it's not that bad. Carry out a previous one, which is carry in, and okay, cool. That looks a little better. Not exactly like the most compact, but whatever. Wow, okay. And now we'll have a 5-bit result out of that here, which we inject to 0. So by injecting a 0, it's just not even worth wiring that up. I'm just going to skip it. We're just going to go like that. And that will come into there. Okay. So now we have this hooked up into that adder. Now we want to take these 4 bits. Nah, fuck, what the hell's going on here? Alright, so now we have this adder. We have the output of this adder, and we have the output of the multiplier. That's right. Or of the, no, the adder, and we have the output of the, oh fuck, that's kind of like not in a good space, good spot. Well, that's easy to rearrange those inputs actually. Yeah, okay, I can easily pull those inputs somewhere else. Because I need to grab those 4 inputs. And I think I need to grab... It looks like I'm grabbing off the 2 least significant bits off the sum of the adder. So let's do that. I'm going to grab the 2 least significant bits off the sum of the adder. And bring them down to join the 2 least significant bits that we previously brought down. So let's grab the 2 least significant bits off the result of this adder. So, and that'll be this and that. So now we have 4 bits there and 5 bits there. What the fuck is going on here? So we take a 5-bit result and convert the top 3 to 4 bits. Oh, because I don't care. Oh, because I didn't use the carryout. Okay, because the carryout's useless here. That's why. See here, I don't have the carryout hooked up. Okay, so ignore the carryout. So we have that. So we have 3 bits there. So we're gonna take those 3 bits and bring them to the bottom of a 4-bit adder. So we're just gonna. Oh, look at that! I have a 4-bit adder right here. Control G. That place is like... I need it like let's do this. And then we'll bring that bus. Excuse me. Shit. Okay. And so now if I do something like that, grab that, do something like that, go like that, 1, 2, 3, 4. Alright, because the 4th bit is 0, it's faked. And then we take those other 4 bits and bring them into there. Which would be these 4 bits. So take 0, like that. The second one is fake. The third one here goes there. The fourth one like that. Okay. And so now we can just we can really just collapse this down to being like this. One, two, three, four, and then we'll get our 8 bits here. Actually, remove that. And then we'll go 1, 2, 3, 4. Nice, okay. So that right there is our 8-bit scoring circuit, or 4-bit scoring circuit. Hello, Johan. Nice to see you. So let's hope this works. Let's put in 5 and let's hope we get out 25. Holy shit, we do. Server set what's the fucking Christ, hold on, let me pull up the Discord. General from wait, what? I'm so confused. Why can't I server I was gonna try to change the tick rate. Why is Discord like not? I don't know, that's weird. Discord's being weird. Alright. So if we put in like 7, we get 49. That can't be right. That was the same thing as before. Oh no, it's not. I shifted it up. Okay. So let's try it. Let's see if 16 plus 32 is 48. Oh, 49. Like that. Okay. Yeah. So 50 is that 225? Hey. Okay, that's fucking sweet. So now let's sync it. So now if we sync this, this is going to be a pain in the ass. So let's look at how... let's get some more selfish playing. And then now I want to look here. So this multiplier needs to be the same delay as these 2-bit squares. Let's just verify that that's even the case. So this is 1, 2, 3, 4 ticks of delay. This is 1, 2, 3. The multiplier is faster than the square. Wait, what? 1, 2. Oh, that's not. Uh-oh. 2 open circuit. This needs 2 ticks of delay. Okay, so this is 2 ticks. 1, 2. So I need 1 tick up there, and then 2 ticks. So I have 1 tick up there to make up for that 1 tick there, which is 2 ticks total. So this is 2 ticks of delay. So we're square, sorry. And this is 3 ticks for the multiplier. So it's 3 ticks for the multiplier, 2 ticks for the square. Fuck. So we need to add a tick of delay to the multiplier. Output. Luckily the multiplier output goes to those right there, which we can replace with there we go. Okay, so now this 1 tick of delay matches the output of the delay of this. Now this adder has 2 ticks of delay. So that means I need to add 2 ticks of delay to the output of the top square. So the topmost bits that get squared, I need 2 ticks of delay. I guess it'd be the top 4 bits here. So now, whoa. I mean, those things look fucking weird, but okay. I'll just space these out a bit. So the least significant bit comes in. Comes down there, we skip a bit. That's not skipping a bit, there we go, that's we skip a bit, comes there, comes to that one, and the most significant bit. So let's verify that this still works. Let's see if we get 49. Nice. Let's see if we get 225. Nice. Okay, still works. Oh, it was the stream thing. Mentions. Ah, there we go. So if I do this, we should now be able to see 8 squared is 64. Okay. So now I should be able to one tick. And now what we can do is build a alright, so now we're going to actually need the sockets. I don't think I need the chub sockets. And now we're just going to line them up. Cool. Alright, so now this is literally just going to be for visualizing what's going on and seeing if it works. So, alright, so we have these lamps things. Alright, that might be a little confusing, but like whatever. Are you fucking kidding me? Alright, so what we want to do is we want to visualize the data coming in. So we're going to say, and we want to make the board stackable. So we're going to say the data coming in then comes to, I guess, we'll do it like this. Check out this. And we'll use a through panel display. 1, 2, 3, 4, 5, 6, 7, 8. Wait, what? Are you kidding me? Oof. So that would all go up there. 4, 5, 6, 7, I'm going to delay it and then reform it back. Alright. G. Now this is like having a scope in Minecraft, except a little bit better. So we can actually see what the inputs are, each tick apart from each other. So now, if I put in the number 4, I better get out the number 16. I better not get any blinks or anything that shouldn't be anywhere else. So that came out as strictly 16. 1, 2, 4, 8, 16. So, okay, cool. So now if I change this to being 36, there better be no weird blinks or anything in between. It should be perfectly synced. Which it was not, and you can see that there. That's because I'm dumb. These 2 bits here don't account for the delay of this adder. These 2 bits here don't account for the delay of this adder and that adder. So that's what I'm going to change now. So now we need 2 ticks of delay. And now this needs 4. What the fuck? Let's go back to just the 4 times 4, see if this syncs back to 16. No weird glitch or anything. And there's 2 ticks of delay, it's still missing somewhere. That's fucked. You can see it. Oh, peace out, Red. Sorry I didn't see your message earlier. I just forgot to have chat up. So is that 3 ticks? Do I need to add 3 ticks to that? How's it going, DJ? Alright, so we're going to go from 6 back to 4 times 4 and see if that generates any weird errors now. Nice! No, no, wait, we're still one tick off. Shit. Let's go the other way. Let's go from down to times 6. This needs another tick of delay on it. Jesus Christ. How am I stuck? Didn't I have... I don't get how I was being stuck before. Alright, let's see what happens now if we turn that back to being 4. Oh, nice! From 36 to 16. Let's go back to 36. So it should just change. There should be no like intermediary step in that. There we go. Perfect. Wow. Okay, cool. So that's synced. So now let's try using the low bits. Alright, so yeah, we set it to 3 times, I don't know what the fuck just happened there. So DJ, I'm working on a modified multiplication circuit and a modified squaring circuit. So here is a 2-bit square, so 1 times 1 is, I set it for 1 tick first. I set it for slow speeds right now. 1 TPS right now. So there's 1, 2 squared would then be 4, and then 3 squared is 9. So there's our square, and then here's a 2-bit multiplier. So you can, and this 2-bit multiplier here uses Vedic multiplication, which is, you can see there's no adder in here. It's a half adder. There's no full adder. So, using some of those modified circuits, now this is, you combine those 2-bit circuits there to make something like this, which is what I have in game now, which is a 4-bit squaring circuit. So now, I'm trying to get this to square. So now when I go 3 times 3, I think I need to add like 8 ticks or another 4 ticks of delay to that. So if I go to 3 times 3, I need to switch that off and switch that on at the same time. But instead, what if I do 3 times 3 to 7 times 7? So that should be 49. So it should be 32, 16, and 1. But now you're going to see it shifts up. Yeah, some more delay is needed. Jesus Christ. Well, yeah, but this is using like an advanced method of computing it. No, I'm not basing it on delay. I'm not basing this on delay. I'm just trying to sync it right now. Yeah, if you guys are liking the stream, if you would please share it, it would help me out a lot. But I think what I need to do here is add like another 1, 2, 3. Yikes. I think I need a lot more delay. Alright, let's hope this syncs it. So now if I go from 3 times 3 to 7 times 7, nope, and then it's going to shift up. So I have to think here. So this is going to be 3 ticks. So we have 3, 3, and 2, make 5. So that needs to be 5 ticks of delay on the output of the top square. Oh, Jesus Christ. Yeah, I need components that can oh my god. Jimmy, this game is going to be very hard to do anything useful with if I can't just tell the delayer how much time I need to delay. Like, there's no, having to rebuild it with a different size. This is not going to be good. Okay. So this is 1, 2, 3 ticks to there. This is 1, 2, now 3 ticks. And then this needs to be slowed down. So it's that, and then carry out. And we inject it to 0 like that. Which we're going to do like this. So now it's 1, 2, 1, 2, and then 3. Perfect. 3 ticks, okay. So now that's synced. This bottom one is 3 ticks. That multiplier is 3 ticks. So then the bottom one with the multiplier comes into here. Why do we add a tick to the multiplier? Multiplier is 1, 2, 3. The multiplier is the faster one. Why did I do that? We're going to skip the bottom 1, 2, 3, 4. So the multiplier has 3. This is 1, 2. Okay, so now that's made 3. So 3 ticks comes in. 4, 5 ticks. So it's 5 ticks into here. 5 ticks into there. Right, so 3 plus 2, okay, so 5 ticks to there. So now we want 5 ticks. We want 5 ticks into here. So we're gonna have to really fucking... That's only 4 ticks, fuck. 5 into there. But that's 5 from... That's 5 from the beginning, but if I have 3 ticks here, that just means 2 ticks. But yeah, okay, that would make sense, just 2 ticks. And I would be able to get... And then skip 1. It's the least significant bit. That comes from there. There. So now that should be synced. So it was 5 ticks to get to here, and now it's also 5 ticks to get through 2, 3, 4, 5 to get into there. Now it's another 2 ticks to get to here. So that means the input coming through there has 2 ticks. So now we need 2 ticks here. Because that 2 ticks is the delay that it would take to come through that right there. Alright, so now I need to count the total delay here. Let's do it, boys. Alright, so we have 1, 2, 3, 4, 5, 6, 7, wait. 1, 2, 3, 4. Alright, we're at 4 there. 5, 6, 7, 8 ticks. 8 ticks total. So now we have 3. Now we need 5 ticks of delay here. Does that make sense? I don't know. We have 1, 2, 3. 3, 5, 7. Wait, 3, plus 2 gives us 5, 6, 7. I'm getting 7 ticks. So 1, 2, 3, 4, 5, 6. How much? Oh, because this one's fucked up on the delay. This one, we need the extra. Oh, okay. Or I just do this. So the least significant bit is that one. And we go there, and then we go there. So now it's 1, 2, 3, 4, 5, 6, 7. 7 there. 1, 2, 3. There. So say 3, 4, 5, 6, 7. Okay, so that makes sense. 7. So we have 3. So that means we need 4 ticks. That makes sense. A multiple of 2, that would make sense because we have this adder and that adder that we're going through. So that would be this. And then we'll just do that like that. Okay. Now, fingers crossed. When I flip the switch here between 3 and 7, it should produce the result 9 and 49 seamlessly. So this bit should not change. These 2 bits should turn off, and that bit should turn on in one tick. Here we go. It's looking promising. Yes! Okay. That moment when you're syncing is like spot on. Like that's fucking so fucking. That's nice. Okay. That's nice. Yeah, it's very nice. Alright, so now if we go up from 3 to squared to 7 squared, we go from 9 to 49. Beautiful. Now if we change from that to 225, it should just be synchronous as well. It should produce this top 3 and leave the bottom one on. Nice. And now to test if this is working, we'll do, I don't know, they say fucking, we'll go back down to 7 squared again on the falling edge. The only reason it was 14 squared is 144. So if we go back to, what is 144 in binary? It's 128. 128 and 16, okay. So it should be 128 and like 16. Oh, I guess I was wrong. And like, wait, what is 14 squared? Times 14 is oh, it's 196, not 144. Okay, I'm dumb. 12 squared is 144. And that's 12, 4. Which we have 12, 1, 1, 0, 0, 0, 1, 0, 0. Okay, cool. Alright. Alright, so now there is our synchronous result. Synchronous 4-bit square with an 8-bit result. That is so nice to see. Now what sucks is I had to use these adders here, and I don't think I can pipeline numbers through these adders at 1 tick. I mean, we can try. Here. I don't think it works though. I'm going to do 3 plus 5 and then switch to 9 plus 7 in 1 tick. So this one will go to 3. Five. This one will go to 7. 7, 3. So we should go. It should get a result of 8 and then 10. And so now if I flip this switch, it does not go. Yeah, it does not go to 10. You have to hold that switch on longer. Oh no, it's because I'm retarded and this carry isn't hooked up. Oh, I need to make sure that carry's hooked up and everything. It's not. That could be bad. Okay. Good catch right there. Is there any other adders? Nope, that's it. Okay. So we're at 8, 10. Is this 1 tick pipelineable? Holy shit, maybe it is 1 tick pipelineable. No way. What if this number was, instead of 3, if it was 9? And then we add, okay, that's okay, so now oh, it didn't turn off. I'm an idiot. Okay, that's 1 tick pipelineable, boys. Holy shit. That means the number could change in here every tick just fine, which is what we were just doing. Holy shit. So let's, okay, so this would be cool. Okay, so let's generate a ROM, or let's have a ROM that will do, that will encode 1 through 15 onto that bus. Okay, so if we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is going to, oh fuck. I need to be wrong. This 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So that will encode 1, 2. This is going to be hard to do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, this is 12, 13, Alright, ROM is almost done. Okay, so now I would like to send a 1-tick pulse. Oh boy, this is going to be interesting. One-tick pipelining in Logic World, boys. Alright, so now if I get a button... and hold that for 1 tick. 1, 2, 3, 4. So it's streaming in. So it should go 1, 4, 9, 16, 25. Oh my god. It's fucking great. Now I don't know how that is staying on. Now that is an issue. What the fuck? Control F2, let's open that up. Now let's post that in the Logic World betas. Stop playing music again, Groovy. Let's take a look at that picture just to verify it. So from right to left, we should look. So we go 1, 4, 9, 16, 25, 36, correct? Oof, I don't know if 36 is correct. Should be 32 plus 4. It derped. One ticking is breaking. Okay. I think that's the issue. I think that's the issue. Wait, I just reported that to the dev. One ticking XOR is breaksome, which explains why that bit is on when it shouldn't be. I think I'm going to try to combat that like this. I wonder. See what happens now. I want to pay attention to this. It didn't turn on when it should have. Oh, there it goes. One, 4, 9, 16. I still don't think that's correct. 36 is 2-4, not 3-4. So we got, and yeah, it's still. What happens if I do 6? That seems to be where it's breaking. It should be 24, not 34 in hex. Yeah, that's fine when I do it by itself. But when I go from... Alright, so we're at 5. And we switch to 6. That's 25. One, 4, 9, 16, 25. It fucked up there. Yeah, it's that bit's getting stuck. Okay. Well, that bit is getting stuck, so that kind of puts a damper on what's going on here. I do not know why that it causes that. I don't know what I can do to get around that. I mean, other than that, it works. Oh, that's so weird. Maybe we get Jimmy on stream. Yeah, I'm very confused on why that won't work. We have a ROM that streams in our value. Excuse me. Alright, I think this calls for a hit from the bong. And I guess in the meantime, yeah, what I'll do is we'll just continue working towards having a 16-bit squaring circuit. So here's our 4-bit, so we have to double this twice. Well, it's a lot more than just doubling, I guess I should say. I need to get all these fucking flies. Okay. Alright, let's see how the stream is doing. YouTube. Live stream. We've got 4 concurrent viewers. Oh, I should probably go like my own stream, shouldn't I? Open, copy video address. Paste. Wait, what the fuck? I'm just gonna like it. There we go. Now you gotta do what you can for yourself. Alright. And yeah. So we'll make a copy of this. Control G. Paste that here. Oof, that took a little while. We're actually going to G and T, or R that, remove it. I don't know if sockets are 1 tick or not. We can try them out. Are those not? Oh, okay. That needs to be on for 1 tick to be registered as an input. That's right. Okay. So the moment that peg turns on, that passes data through. Okay, I see. So 0 tick. Cool. So I'll leave those there. No point taking them off if they had no delay. We will now remove this. R, G, R. GR. Cool, and now we're back to just that without all the bullshit. So now what we need to do is we need to go back to, go to this page here. Alright, so we have this 4-bit square here. And now what we need to do is continually build on itself. So we have oh shit. Alright, similarly, the 8 and 16-bit and 32-bit squaring circuits are designed and implemented using a recursive Vedic multiplier module and squaring module circuits of 4-bit, 8-bit, and 16-bit respectively. So let's take a look at this. So we have our 2 by 2 multiplier, and this is, so that leaves us with 8 bits. Adder. Okay, so I see what we gotta do. Okay, so this is the recursive unit. I see what they're saying. So we have the 2-bit squaring circuit and we have the 2-bit Vedic multiplier. So now we have to make a 4-bit 4-bit input Vedic multiplier, and then we'll have our 4-bit squaring circuit. Then we're going to replace these blocks with 4-bit versions of itself. This will then become an 8-bit shifter, yada yada yada, and all the logic will continue. Alright. Man, it's cool being able to just interpret shit like this if you look at it long enough. I remember being like fucking like, I don't know, like 16, 17 and thinking to myself, how am I ever gonna fucking know how to do this shit? And now you just look at it and just know how to do it. So yeah, let's make a 4-bit Vedic multiplier. So to do that, this is the design here. So we're gonna need two 4-bit inputs here, like you can see here, A0 through A3, B0 through B3, and we're going to be splitting them off into those 2-bit multipliers that we built. So we need the bottom 2 here, the bottom 2, the top 2, top 2, bottom 2, top 2. So I think that's exactly, yeah, I'm just going to lay them out. Maybe I'll stack them vertically? I'm not sure. Oh no, I'm definitely going to have to do them horizontally. So let's just grab these 4-bit Vedic multipliers. We'll make a new board, paint it, X, we're gonna, how do I change that? Oh, okay, like that. Let's lighten that puppy up a little bit. That's not pleasing whatsoever. Oh, fucking Christ. There we go, okay. Oh, that's not very good either. That's not very intuitive. So now we're going to need 4 of these. Control G. I actually think I want to arrange it the way... Alright, well, let's just grab 4 of these. I will move these closer as I use them, but I just want to get the idea laid out. So these two do the... Okay, oh shit, so no, I'm definitely going to have to... Shit, I don't even know I did that. Let's just grab them from here. Yeah. How's it going, Crispy? Thanks for joining. One, two, three, four. Alright, so now we need the rows. This will do top row. This will do bottom row. This will do leftmost column. And this will do rightmost column. There we go. Okay, so now we have our inputs. Now we're going to yeah, so now I'm just going to grab okay. Yeah, I think that's as close as I'm going to go. So I'm going to have two 4-bit numbers. Two 4-bit numbers. So 1, 2, 3, 4. 1, 2, 3, 4. We will label this B. Okay, so A. Now we need the first. All right, wait. Well, let's copy all these multipliers. It feels so weird working with 2-bit multipliers, but yeah, this is how we're gonna build a 4-bit multiplier. And then using the 4-bit multipliers, we will build the 8-bit multiplier. So it's just reducing the amount of area. So now we don't have to build that huge fucking triangular thing. Oh, that's actually really nice. That's actually really, really nice. Okay, I see now the advantage of this, because it's hard to see at first. Anyway, so now we're going to work our way from right to left here like this. Like this one's the rightmost and that one. So we're going to be looking at it like this. So the inputs here will be A gets 0, so the bottom two. So bottom two, or no, I gotta refer to it as A, B. So bottom two, top two, and then, okay, so for the first one, we're just gonna bring in the low 2 bits of each number. So for the first one, we bring in the low 2 bits of each number. Like that. The second one, B gets the bottom two and A gets the top two. So B so we're going to call the bottom two inputs B. So B gets the bottom two, right? B gets the bottom two off of the one called B. Right, I believe so. Yep. B gets the, and then A gets these two. Now the A input gets the bottom two. So now we're going to see the bottom two go up here. And then the top two of B go into this. And now I'm pretty sure it's the top two of both. So now we can take the top two, which is that here. And we can take the top two. Like that. Whoa, that definitely cannot be right. I definitely think I just messed something up. Yeah, I did. So now it's going to be... There we go. Okay, so now those inputs are broken up. We're going to take the bottom two bits. Hey, what up? How's it going? I think that's Omegang's Bad Redstone Gopher. I think that's Omegang's, but I'm not sure. Anyway, I can see why this advantage is so much better. Because each stage of the adder you do, or of the multiplier you do, there's two adders. It's a fixed two adders every stage you do that you add new to the multiplier. Whereas each doubling of the bits on a Wallace tree multiplier didn't just add two adders. It added, well, if you had if you're going from say 32 bits to 64 bits, it would add a shit ton of adders. Whereas this, if you're going from 32 bits to 64, it still only adds two adders worth of delay, two in parallel with each other, and then one is in series with those two that are in parallel. So it's really only two worth of delay. That's insane. Like, oh my goodness. So the wiring for this design is shit. Like, it's hard to do. So I don't see it ever being like used in Minecraft. But like, this is totally doable. Like using CCAs or CSAs in Minecraft, carry save adders, and then you can 2-tick pipeline it. We're close to 1-tick pipelining. No, Omeganks, it's not that, because each stage relies on the delay of the previous stage, so... And then I don't know. Alright, so you can see the stream, right? So each one of these 2x2 Vedic multipliers basically has... is basically like... Inside of one of these is this, so like it's fractal-like, basically. It builds on itself fractal-like. So like if I go to the next slide here, you'll see that so this one back here produces a 4-bit, so it's 4-bit input, 8-bit output. The next one then says take your 8-bit output here, and now we're going to make a 16-bit output. And so you could just keep taking that design and stacking it on itself like that. So I'm not really quite sure what that actually works out to being. But yeah, then I'm going to go as far as making the 8x8 one here. So it's going to be a lot of steps here for cursivity. So far I've only, we're working with the 2x2s. So this thing's going to get pretty big at the end, but in a different fashion. So yeah, now I need to grab the bottom 2 bits off the 4-bit result. And that's going to be 4 ticks of delay that I need to add, because there's 2 adder stages. So we're just going to I wish they automatically connected like when they were that close. Okay. So now the what is that, a 4-bit adder? Yeah, 4-bit adder. Oh, that's right. I need to check my circuit here. File, open recent, 4-bit adder. So this is it here. So I'm saying take the. All right. So yeah, it's a 4-bit adder. We're injecting zeros onto the top 2 bits. So I need a 4-bit adder. I'm so glad I built most of this in digital beforehand, so I could just have like a quick way. Alright, so I need that 4-bit adder, which is like right here, which I showed that this 4-bit adder responds to like 1 tick. Like, do you see this, Omega Gangs? So in here I have a ROM that switches between encoding 5 plus 3 to encoding 7 plus 9. So it's going to produce 8 and 16. So if I put a button on here and hold this button down long enough so that it gets through like that, you see that it switches to 16 back to 8 in 1 tick. So like it's calculating all the carries through the carries and switching at 1 tick. So like even though it's 2 ticks of delay in the adder, we can pipeline at 1 tick. There's one issue though. Check this out. Like when I click this button will put every tick, it'll encode a new number in, so it's going to count 1, 2, 3, 4, 5, 6, 7 up to like 15. So it's going to count 0 through 15 every tick. It'll increment, and you're like this. Yeah, this XOR is going to get stuck on because it's not really super compatible with 1 tick logic yet. So this is squaring. This is going to square the numbers 1 through 15. Every tick, it's going to square a new number. So each one of these screens is separated by a tick. And it fucks up because this is fucking up here. Occasionally it fucks up like that. It's stuck on. Like zeros are coming in. Like 0 squared is 0. And this is just stuck on. So like the moment that I fuck with that input, it'll go away. So Jimmy's got to fix that. So we can't do 1 tick pipelining yet, but we can at least still do 2 tick pipelining if everything is synced. But if he fixes that bug, then we can do 1 tick pipelining, and like that's literally double the throughput with no effort. Like it's still synced. Who cares? Because there's none of that repeater crap. But if he adds, but as long as you use those 1 tick repeaters, you know, like you can't like if he adds the delay the way he wants to do it from multiple like ticks, a 2 tick delayer will only respond to a 2 tick pulse, which kind of sucks. Like in my opinion, you should take that 1 tick pulse delay for 2 ticks, and then output a 1 tick pulse. So you're gonna need to stick to just using like 1 tick delayers for most of your timings. Yeah, I set it to 1 tick per second just so I could visualize what's going on. But yeah, you can run it like thousands of ticks per second. But then like syncing, yeah, of course it's gonna look synced. It appeared instantly on the output. I mean, here, watch. What's the server simulation? Alright, ready? Like, you can't even see, like, it's just too quick. Like, good luck actually telling what's going on there. So, like, it's So I set it to 1. Just so I could see, like, it literally 1,000 times slower, just so I could see what the fuck is going on. So it's just like a debugging tool. But yeah, it just kind of pisses me off that that gets stuck on. And that's the only one doing it too, which I don't understand why. Like, maybe it's because it doesn't like the input off the relay. I mean, it's stuck on even without a fucking... Let's do some fucking bullshit signal passing here. Logic circuits go brrr. I separated so that pin isn't tied directly to there anymore, seeing if that's the issue. And we'll see if it gets stuck. It's looking good. Nope. It turned off. Wait, that fixed it. Whoa. Yeah, thanks, Philip. Yeah, it's pretty cool. Let's see if this produced the right result now. So we got 1, 4, 9, 16, 25, 36. That fucked up. The next one fucked up. Oh fuck, I didn't realize it was loud in here. Yeah, I can, am I too quiet or am I too loud as well? That probably fixed a lot of the noise. Control F2. So we got 4, 9, 16. 16 plus 9 is 25. That's wrong. And I don't even see 225 come through. Oh, 225 is the last one. 225, that worked. 14 squared. Yeah, I think there's fuckery going on with the 1 tick. I guarantee you if I change, what sucks is if I want to do 2 tick, I need to offset everything by 2 spaces to fit 2 ticks of delay. Or I need to like add, yeah, it just becomes such a fucking cunt. And then I have to add to make all these 2 ticks. And I can't just right click to add more delay to each one of these. Like, this makes it so hard to do things. I hope Jimmy is seeing this because, like, we need to be able to change the delay on here, but we also need it to not affect the way the pulse is seen. Like, I don't know how else, like, otherwise these circuits are gonna get huge and, like, unbearable. Okay, so anyway, back to this. So I need a 4-bit adder. That's what I was doing. Oh, that's right, I was grabbing a 4-bit adder. Which is this here. Shit. Alright, so we need to add the bottom. We need to add all of. Okay. So we need to add all of these 4 bits. I'm gonna do this. Grab it by that, by its little tail. And I want to be able to get inputs to it easily, and we can move it afterwards, which is nice. So anyway, so this is going to be 1, 2, 3, and 4, like that. And then the other inputs are going to be the bottom, or the top 2 bits of the other one will be the bottom 2 bits of this. So this will be 1, and then the carry out will be 2, like that. Sorry, stream. So we added those 2 values together. So now we need a 6-bit adder, it looks like. So let's Control G. Remove that. Remove that. Control G. Remove that. Remove that. That hooks up like that. Carry out from that plus that. Carry out from that plus that. That and carry out. Alright, there's our 6-bit adder. I freaking love relays. Having expandable sized adders like that. There we go. There's our 6-bit adder. Alright, so we need to 6-bit add. So we're going to take the result of this operation, which is, so we're going to inject 2 zeros. Alright, so bring the multiplier all the way over, or the adder all the way over to the rightmost multiplier. Fuck. Kind of preferred tongues controls for this. because this is driving me nuts. Oh, oh, oh. I think that's as good as I'm going to be able to get it there. Actually, that's probably a little too close anyway. There we go. Wow, okay. So we're going to inject 2 bits to the bottom, and then the rest will just come on. So this will go like that, like that, like this, and then hopefully that bit can reach it. Fuck. Alright, so we'll do this. That can definitely reach, okay. Okay. And now the top 2 bits don't get used for the other inputs, and we tie the bottom 4 here. So it might be a little bit more convenient to have them here. So bring that there. Bring that there. That'll make that a lot easier. So now we have the least significant bit that comes after. We have that bit, and then we have the carryout. Nice. So 2 ticks there, 2 ticks there. So we have our first 2 ticks. These will get summed again. That will be our second 2 ticks, which are synced with that right there. So actually, I guess let's remove that, and let's just keep the delay with where the delay actually is. Just keep it working like that. Also, what time is it? Let's do like a stretch. I've been streaming for a little bit. I think it's probably a little bit healthier to do a stretch right now. So let's just pull up a schematic or something. Tap on the screen. Stand up. Stretch out. Take a hit from your bong if you have one. Feel free to join me. All right. So we have this adder hooked up. We now need a 6-bit adder again. We're going to add the result of those two adders, or those 2 multipliers. Oh no, those 2 adders, yeah. So we're going to just do this to get this to wrap around. I'll just tie these back here like this. And then what we can do fill in something like that. Control G. Something like that. So the 4-bit adder here, the top 2 bits just become 0, so they're just not used. So we only need these bottom 4 bits here, so I should also grab this one and that. Those 4 will go 1, 2, 3, 4. 1, 2. Shit. Okay, let's try this again. One goes there. 2, 3, 4, like that. Okay. And then the other inputs here, we need to get out 1, 2, 3, 4, 5, 6. And we can just do 1, 2, 3, 4, 5, 6. Control select, and then control and select. That doesn't work. 1, 2, 3, 4, 5, 6. Control select. Nope. Control select. There we go. Let go. Control. Control select. Let go. Control select. Nice. Okay, so now that's 2 ticks and that's 2 ticks, so that's there. Alright, so I guess I shouldn't have deleted these because like, you really can't see it. But we'll just add another 2 ticks for the other adder. That's not too big. I actually kind of like the way that fits. And then there's going to be 4 of these for the next larger one. Okay, that's actually going to be pretty sustainable. It's not going to be too large. Actually, that's what reason this is used, is because it's the smallest in terms of complexity needed, I think. So now if we want this to be, I don't know, consistent, and just put on our 2 lower bits. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now let's try this. This is gonna be interesting. 1, 2, 3, 4. Fingers crossed. Let's do 5. Nothing comes out, I hope. Good. Times 5. Set for really slow speeds. Oh, we're close to being synced. Really, really close. Something's off, but we're close, and that's a good sign. But there's 25. Now let's try like 15 times 15, see if we get 225. Oh, the reason it wasn't synced is because I literally have to flip the inputs. Okay, I'm an idiot, so that's why. And we're at 225 on the output. That's beautiful. Okay, so let's see it. Alright, let's test how synced this is. This should be 49 on the output. So we're at 49. When I flip the switch, it should just go straight to 225 on the output. There should be no fucking around. That's beautiful. Okay, it is synced. Okay, synced on the first go. I am a god. I am a god. You know, that's what it feels like to be a god. Just letting you guys know. Wait, now instead of jerking myself off, let's move this. Let's like make a copy of this before I start fucking with it. And now let's try to move this. I love how you can do that. Oh, Groovy left. Okay, so we have an 4-bit multiplier there. That's kind of cool. So it's 1, 2, 3, 4, 5, 6, 7 ticks of delay. So it's more delay than I would have from just a matrix multiplier, I believe. Where don't I have? Didn't I build one of those? Or did I delete it? Oh, here it is over here. Yeah, because if I was doing this for 4 bits, it'd be 2. Yeah, it was like 9 ticks for my 16-bit multiplier. Using that, so like maybe this isn't faster, but it's just less space. All right, well we'll see where this goes. So I think now. Yeah, this is telling you 2 bits at the top, 2 bits at the bottom. Yeah, this is 4 bits and they're putting 2 bits at the bottom. This is 4 bits, they're putting 2 bits at the top. This is a 6-bit adder. This is 2 bits. No. 3 and 2. Yeah, 2 bits and they're putting 2 bits at the top, so that's a 4-bit adder. And this is a 4-bit result. So that's how you can read that. What's going on there. So now when we move up here to this, it's like the same thing. Except now we're going to take 4 of our things here. So now we're going to make a big ass board. We'll color that like piss yellow. Like an even pissier yellow. Nice. And we'll grab that. And then eventually what I'm going to do is I'm going to turn this whole thing on its side and make it just a vertical stick of just like fucking multiplier. Alright, this is starting to look pretty fucking fractally. You can see the four of the individuals and you can see that. Alright, so now what I'm going to need is obviously 4 wide, but 8 input. Well, that's what I need, 4 wide and 8 inputs. So, let's get going. Here we go again, boys. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. We will label this B. Make it big. Label that A. Make it big. Okay, so now so we get the bottom 4 to A and B on that, so B goes to B. So bottom 4 of B, bottom 4 of A to that. So bottom 4 of B, so bottom 4 of A. Please reach. Nice. Now we need the top 4 of A and the bottom 4 of B. So we'll take the bottom 4 of B first. Now we'll take the top 4 here, like that. Okay. Now we need the bottom 4 of A to go here. And then we need the top 4 of B to go there. And now we need the top 4 of A. That was A, right? And that's B. Top 4 of B. Now we need the top 4 of A. So easy with the wiring like that. Alright. The wire splitting, easy in Logic World, hard Minecraft. Okay. And now we need a... This is taking 8-bit, so now we need an 8-bit adder and a 10-bit adder. And, well, guys, I'm going to grab some more coffee, because that's what I gotta do. Be right back. If you're enjoying the stream, please leave a thumbs up. It helps me out a lot, and please like and share. Well, obviously like, I just said that. Alright, sorry about that everybody, I'm back. Alright, and we're about to get into it again. So, we have our input. This is such a lovely diagram, but I'm starting to understand how it works now just from building it. I don't think I would need an example going from 8 to 16 after we get done with this 8, but I'm going to use it still. Although I think I'm going to stack in a different manner to utilize space more efficiently on the next one. Hey, how's it going, Paul? Paul, Josh? Here, I didn't recognize you because your fucking picture's black. But anyway, here we go, boys. So we need an 8-bit and a 10-bit adder. So we're going to grab this, Control G, it's easier to build when it's flat, so I'm going to do that. I'm going to remove that, and that's already removed. So we have 1, 2, 3, 4, 5, 6. So if we Control V, Control G, if we do this, so now we have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's our 10-bit, and then we'll Control G. Ah, shit. So we actually have to get that to adhere. I'm going to make that the terminology used, adhere, by sticking it like that. And now when I clone up this board, now it's there. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we can remove these two like that. Okay, so here's our 12-bit and our 10-bit adder. Still only 2 ticks of delay. So what we gotta do is we're gonna use the 8-bit adder, and the 8-bit adder is going to be hooked up near the output of the second multiplier. So the output of this guy, we'll have the 8-bit adder sitting like that, I don't know, like somewhere there. So we're going to Control G, and Control G for Jesus. Alright. Alright, this is going to be a pain in the asshole, isn't it? Yes, it is, and I see why. Alright. I like how it says you can't place it there, but you really can. Hey, what up, Slick? How's it going, Slick? Thanks for joining. I like when you show up. It's nice seeing you. Now I can grab it. There we go. Oof. Alright, so now to connect this up, we've got to go... These 2 bits go there. Oof. Like this, there, and then these ones go there. And then we're just going to inject, so out will come, we're going to take the top 4 bits here and we're going to inject, what the fuck? How are they only injecting 2? Well, I guess we'll see what happens. So we will, I'm not sure which way I want to do that now. As this is a 10-bit adder, because we're taking 8-bit let's look back. Yeah, so they're injecting 2 bits. That should be injecting an 8-bit and a 12-bit adder. I'm using a 10, 8, 10, and where are they using it? Oh, they're using an 8-bit adder here and 12-bit adder here. Okay, that makes sense. But I don't understand why they'd be injecting zeros. That'd be a 10-bit. I'm very confused here. What did we do here? We injected 2 zeros at the top and 2 zeros at the bottom. Here it's saying okay. I'll follow. I'm confused now. Alright, so I'll take the bottom 3 bits off the first multiplier. Bottom 3 bits go through. The bottom 3 bits would be that, okay. Then all of those no, shoot. All of those oh, because we threw off 4 bits here. We have 4 bits. We should inject 4 in the top, I believe. I think that's just a typo. I'm going to throw 4 on the top, and we're just going to inject to the bottom of the adder. Okay. So we have a 12-bit adder here. I don't understand. If this is a 12-bit adder, are the inputs 12 bits? 8-bit Vedic multiplier. Eight-bit using Vedic. Okay. So we take this to top. Okay, this is much better with like less of the weird shit with the injecting. Okay. So now we take the top 4 bits there. So when you add 8-bit numbers, you're going to get this. It's going to produce a 9-bit result. I don't understand how that's going to be a 12-bit adder. So this is what we have. We have the 3. We're going to take the top 4 bits, bring it into what the fuck? Nope. Okay, maybe, yeah, they're just retarded here. They're just absolutely retarded because in this they update the amount of zeros that they have to inject in places. Oh, it cuts off the bottom. That's fucking lovely. Yeah, so then there's going to be 4 zeros injected at the bottom here. And that means 4, so this is going to be a 12-bit adder, so that's why. These fucking assholes. So it's an 8-bit and these are 2 12-bits. It just doesn't tell you that shit. So we have our 8-bit there. Which is what, I guess that's a replica of what we did in the other one. It was a 4-bit, and then 2 8-bits. So here's an 8-bit and 2 6, yeah, whatever, same deal. 8 and 2 16s or some bullshit. Or 8 and then a 12, or whatever, you know what I mean. Fuck. So let's do that. So we have an 8-bit adder. So we hooked up the 8-bit one correctly. We injected zeros at the bottom, or at the top. We injected 4 zeros there should be, so the top 4 inputs should not be. Well, fucking hell, what the hell did I do here? Alright, we're gonna redo this. So we have, oh, it should have 4 bit, oh, I'm retarded. I'm so dumb. Okay. So we're going to 1, 2, 3, 4, ignore those, and we're going to take these 4, and they're going to go 1, 2, 3, oh. I see the issue. 1, 2, 3, 4. Okay, we take those top 4 bits. Then we need to delay those bottom ones. Well, I guess we'll get there when we get there. Alright, so that's now done correctly. Jesus. Now we need a 12-bit adder there and a 12-bit adder there. So not 10. So I need to go back to 8. 1, 2, 3, 4, 5, 6, 7, 8. Control G. Excuse me. Okay. So there's our 12-bit adder. So now what we're going to do is stick it all together. I love how like this is shit that like graduate students do. And like fucking they write like all these high-end papers and try to make it like all this exclusive shit that makes it hard to understand. And you can sit here and fucking build it in a video game. Like, yeah, I may have a fucking bachelor's in computer engineering, but like, if you just know what you're doing. Alright, for anybody who's listening, like basically in college, like for electrical computer engineering, I tried to do the computer engineering route, and by tried to do that, I mean I took those classes, but I didn't learn a single fucking thing because I already knew basically everything they were teaching me specific to this, because I've been doing it for so long on my own, that it would have been better off taking the electrical engineering route and taking all the courses that I didn't know dick shit about. Because the ones that I knew dick shit about, I was lazy and I didn't, like, I got B pluses and shit, but I wasn't getting A pluses because I was just lazy and I didn't care and I didn't like the way the teacher was teaching stuff. But in the courses that, like, you don't know stuff and you're just taking it the way the teacher teaches you is the way you're learning for the first time, so that's the way you're going to do it. Like those courses you can do a little better in when you don't have that way of just, oh, I know how to do this, I'm going to do it on my own, fuck their way, my way's better, you know. Because you know no other way. Yeah. But I think a good example of that is I took like Analog Electronics 1 and Analog Electronics 2 where you build like transistor amplifiers. And like I got A's in that class and like I'm not that great at that stuff at all. But it's just like you don't need to be that great, like, you just need to work hard. Like, knowing it already, like, that predisposes you to being lazy in the class and not doing good. So, like, I didn't know that shit. I had to work hard. I did well in the class. It's just like that. So, I mean, you just have to pick and choose. So now we're going to take our 12-bit number, our adder, and we're going to stick it like right around here somewhere, where those values can easily get. Yeah, we'll do it like that. I wish I can like rotate by like not angles of 45 or of 90. I wish I could do like 45-degree rotations like that. That would be nice. But yeah. So now we have that 8-bit output, and we're gonna inject 4 zeros on the bottom. So we're gonna take this 8-bit output and basically bring it. So I'm gonna the easy way to do this is copy it like that, and then go like that till you're out of buses, like that, and then these two come there, and now there's 4 zeros injected at the bottom. That's exactly what we did. It only shows 2 there because this diagram's like really piss poor compared to the next bit for some reason. I don't understand. Well, I understand the diagram, but I don't understand why that would be that piss poor. because if you look at the next one, it clearly shows that we inject 8 and then 8 at the top, but we inject 4 in the last one, and now we're going to inject 4 in the top. So we injected 4 at the bottom there, and now we're going to inject 4 at the top. So we're going to take so what's the other input to that? It's this guy right here. So we're going to take these 2 bits. They go here, and then now we need to add okay, and now we can select that, paste it in here to our out of buses, and now that's 1, 2, 3, 4 bits at the top that we left. So now we injected 4 zeros at the top, and so now we will use a 12-bit adder to add those numbers together. So what I need to do is like grab all these values off the back, which doesn't reach like that. Of course it doesn't. Okay, I'll take those 8 bits. So fuck. Come on, stand up. I'm wondering where I can bring this. How close? What's limiting me where? Alright, I think right there is probably like as close and as lucky as with that as we're gonna get. Alright, so I learned now it's like N and M to get that there. I like how it's 3 adders per module. Like, that's so nice. So every doubling adds 4 ticks of delay. That's insane. Alright, so So now there should be 12 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So now we're going to take the, let's see how they do with the 8-bit one. So you just take, oh, you just add them all together, yeah. You don't have to fuck with anything. Low bits go to low bits, high bits go to high bits. Alright, so let's hope this fits. There to there, nice. And then the 8-bit adder. Hmm. 15 down to 4. Okay, so then these just become the low bits there. I don't know what just happened. Okay, that was weird. Of course, there's more issues. Two, three, four. Okay. So now we should have a. We have that, but oh, fucking Christ. Alright, so we need to actually shift this up by. Well, we have 4 bits, so that's 8 that we need to shift it up by. So we will 1, 2, 3, 4, 5, 6, 7, 8, and we will grab that by that N E place. Beautiful. Oh, that's so nice. Being able to do it flat but vertical at the same time. Oh, that's so nice. For anybody watching, I hope you're impressed, because I am. Okay, so now we need to add 4 ticks of delay to these. 1, 2, 3. There should be like a feature for auto-connecting those motherfucking things. Like an option that just says, when placed into X close, do you want them to connect automatically? Yes. One, 2, 3, 4. Okay, so now cool. Now we'll do this. 1, 2, 3, 4. And we can do 1, 2, 3, 4. Just like that. Now it should be synced. So now let's try, well, to test how synced it is, I'm just going to use one set of inputs and tie them both together and treat it like a squaring module, so that when I flipped one input, it switches both at the same time, just to make things a little bit easier, so I don't have to set up a circuit, which, I mean, isn't that hard either, but I just don't want to right now. Hey, what up, Bro Yojo? So I don't know if you heard, but this is a way different multiplication algorithm than what we're used to. This it makes it easy. It uses less area than a standard Wallace tree multiplier, and it's pretty linear. It uses 3 adders each time you double the width. Although the width of the adder obviously changes as well. Oh, is it? Okay, yeah, I will. I wonder if I can do that right now while I'm live. Let's see what happens. So, settings, stream output, streaming, target bitrate 3500. So what should I change that to, like 5,000? Well, let's see if that did anything. Well, yeah, I hear my computer actually trying to work. Let me know if that changed the quality at all, noticeably. And if it did, maybe I'll try a little bit more until we get to a point of no return or something. Or of no returns, I guess. Diminishing returns. Okay, so let's try doing, let's see if anything broke. 15 times 15 should still make 225. $18,000 while I'm streaming? I'll go up to like 10 grand. Anyway, so 15 times 15 still produces 225, so nothing broke on that end. Because it was just copied. Okay. So now if we do 225 times 225, let's get that calculator out. That was not, oh, well, it was me flipping through the levers, okay. So, 225 times 225 is equal to, oh wait, what am I doing? It's 255 times 255. 65025, which is FE01. So we have, you can break it up like this. F E oh, because I put that in the wrong spot. There you can see FE01. That's 225 or 255 times 255. Yeah, I switched to 10 grand right now, so hopefully that's working. Is the video quality like better? Like our edges like sharper? I don't have like great anti-aliasing on. Oh, okay. I clicked apply on OBS, but yeah, who knows. But yeah, this is fucking cool. This is a So there is how much ticks to delay? There is 4. 8, 9, 10, 11. 11 ticks of delay so far for 8-bit times 8-bit. If I double it to 16-bit times 15-bit, that's going to turn it to 15 ticks. And 32 by 32 will then be 19. Damn, that's fucking beautiful. Oh, I want to get to that 16 by 16 size. Alright, well this works. Oh, but is it synced? That's what I have to check. Oh, fucking idiot. So I have it set to the speed. Yeah, I'm about to sync this. So now it should be doing. I have it set for 1 tick per second right now, so it's. Alright, so it's done calculating. So we have FE01. So I'm going to now tell it to square 14 times 14. So, Bro Yojo, the reason I'm doing this is I need an efficient multiplier for Mandelbrot, one that uses like a lot less components that would normally be used in like a bigger multiplier. Like a Wallace tree multiplier would have a lot more adders, and those adders have more relays, and those relays, even though they're quick, will cause more lag in the game because of the way they're coded. So I want to take advantage of using relays while using less of them. So now what I'm going to do is I have 14 squared, and now I'm going to make it do 15 squared, and hopefully on the output here there's no blinking. It literally just switches from whatever it is now to the right answer, which is FE01. So the bottom shouldn't change, but the top 8-bit should. Nice! Okay! Synced! Yeah, syncing this is super easy. So now to double this one more time, we need 4 of these. So I need to control G. Wow, that was quick to grab, but I don't know how quick it'll be to paste. Wow. Wait for it. Can I interact with the world yet? There it is. Okay. Not bad yet, Jimmy. Yeah, Bro Jojo. The other thing that's cool is I discovered, because Red CMD has been screaming at me, that there's a simplified circuit for doing squaring. Like if you just want to square 2 numbers, you don't need a multiplier, because then you would have a multiplier with 2 inputs and you tie the inputs together, and that's fucking dumb. Like there's got to be a way to do it with just 1 input that just outputs the square of the input. And so there's this. So 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. And then 3 times 3 is 9. So there's a 2-bit squaring circuit. So you're using this 2-bit squaring circuit. You can then make a circuit that squares. So this is a 4-bit square. So you input, say for instance, the number, or what the fuck? Alright, so I can input like 12 and square it, and 12 squared will come out of it 1, 2, 3, 4, or 3, 4, 5, 6, 7. 7 ticks later. So what I need here is I need that special multiplier called a Vedic multiplier right here, VEDIC, Vedic. So that's this right here for 2 by 2, and then I need copies. I need the 2 by 2 square here and another copy here. So two 2-bit squares and a 2-bit multiplier make a 4-bit squaring unit. Now I'm going to need 2 4-bit squaring units and a 4-bit Vedic unit to make an 8-bit squaring unit. Then 2 8 bits and an 8-bit and so on and so forth. So they're going to recursively like grow. So I need like, that's why first what I'm doing right now is laying out all the multipliers that I'm going to need. So here's the one with the 4-bit inputs. Then you take the one with 4-bit inputs and make the 8-bit input one. And now you're going to take 4 of these here and make the 16 input one. So I'm going to recursively grow these, which feels pretty fun. And so now I think the last color that I should make for my... I mean, that fucking... I pretty much spot on made this thing like the right size. Holy shit. Alright. That's insane that it just happened to... Like, Jesus. I didn't even know. Alright, so now we just need a huge one. Alright, now, how much let's go, like, eat red. Like somebody, orangey, I don't know, that's too close. The colors that I'm seeing here isn't really matching what's on there, but, okay, Jimmy, whatever. Now I'm wondering if stacking on top of itself would be the smarter idea here. Wow, that's nice. Okay. Would it be smarter to now One, two, three, 4, 5, 6. Wow. This is insane. Not very dense. Oof. Oof. Uh-oh. Please don't tell me it corrupted. No, it's there, okay. Jesus Christ, boys. Y'all are in for a treat. Why can't I resize that? That doesn't make any sense. Oh, good thing I didn't go too big. Jesus. Well, you know what you gotta do. What the fuck? What the fuck just happened? Uh-oh. Okay. It's still there. Not broken. We need our through pegs. There we go. Through pegs. And we need 16 inputs. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16. I need a label. Alright, so now got to do the same thing, ladies and gentlemen. So now we're going to have 16-bit inputs. So the 16-bit inputs are represented by so we have B15 to 8, B7 to 0, B15 to 8, B7 to 0, B15 to 8, B7 to 0, so you can see that. And then A the same way, so that's 16 bits, 15 through 0 is 16 numbers. So now it's showing you the bottom byte and the top byte of each one. Excuse me. So it's telling you where the bottom byte and the top byte is going. So we're going to say that we're going to go so the bottom right here will be bottom, so we're going to take the bottom 8 bits of each one. So bottom 8 bits of B here go to the bottom 8 bits over there. So 1, 2, 3, 4, 5, 6, 7, 8. So we went from the bottom, and they're going to go here. 1, 2, 3, 4, 5, 6, well, hopefully. Wait, what the fuck? Let's do that. What the fuck? I really don't know what the fuck just happened right there. But we're gonna try again. Oof, and now I'm destroying shit that I didn't mean to. I hope I didn't delete anything else, because that would literally fuck me. We need an undo button. But Jimmy can't save state of the game, I don't think. I don't know how we would fucking do that. One, two, three, four, six. 1, 2, 3, 4, 5, 6, 7, 8. And now the bottom 8 of these should be input A. Fucking hell. Okay. So bottoms go there. Now we're gonna say the bottoms of B go to the left one. So B. So we'll send the bottoms of that. So we'll send there to there. Now this gets the top of A. Okay. Now the other one here will get the bottom of A. So now we have A here. Say bottom of A. Comes there. The top of B. And now the tops of both go to that side. So top of B. Very cool. Okay. Now, of course, we need those fucking adders. And this is why it's so important to have one module synced before you move on to the next. Because it relies on 4 of the previous to generate the next. And then you can see we have 1, 2, 3, 4 buses or results. So it's basically going to be adding these two, those two, and then a final adder. I kind of want to grab some more coffee, so, well, that's what I'm going to do. I'll be right back. You've been watching the Wild Drive-By stream. Boy, my computer puts out a lot of heat. Anyway, hope everybody's still here enjoying the stream. We have to now hook up a very, very big multiplier. Alright, so we're going to take the bottom 8 bits off. So the bottom 8 bits are up to there. We're going to take those off and not use them. We're going to take, then what that means we need, saying 12-bit and 24-bit adder, but last time I saw what they wrote for what they needed for adders, they were very, very wrong. Yeah, I don't know what these idiots are talking about on this page, but like none of this is right other than like the diagram slightly. Glad I'm not an idiot and I can understand what's going on. Yeah, so we need a 16-bit adder there. And a 24-bit adder. Well, you know what that means. Let's make it 16-bit and 24-bit coming right up. Wait, why am I coming here for that? I have a copy over here. Control G. Oh fuck, that's right. Okay. So we have, I don't know, Control G, I think that 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Is that 13? What the fuck? I think it's 12. So we need a 16 and a 24-bit adder. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 20, 21, 22, 23, 24. Okay. So now we make to go from 24 to 16, so G. Gotta find the spot where it broke right there. Amend it. Do the same over here. Find the spot that broke. And amend it. Alright. So this should be our 16-bit adder here. So now now we need to use our 16-bit adder, and that's going on the bottom layer here. Okay. Are you fucking kidding me? Okay, so we took the bottom 8 bits off. That means the top 8 bits are going to go into the bottom 8 bits of this. So the top 8, 1, 2, 3, 4, so this here. Hey, I'm building a weird new multiplier that I've found called a Vedic multiplier. Oh boy. Yeah, so the Vedic multiplier is like it's the beta. Pink. Nice to see you here. I'm testing it out, running into bugs left and right. Anyway, so I need the top 8 bits here to go to the bottom 8 bits here. Like that, nice. Alright. And then now I need 16 bits out of this to work over here. Oh, that's not gonna work. I need to... Did that fuck up happen over here? Oh no, it couldn't. Okay, because of their outputs. 1, 2, 3, 4. 1, 2, 3, 4. Good. I'll grab the rest. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I put the wrong... Is this the 24-bit one? Yeah, I'm retarded this way. Neat. Okay, that makes more sense. Right now it's actually, he just put out an update in the beta, which is why I'm streaming right now with it. And the idea was to fix the lag with the big machines, and it seems to be alright. I mean, look, this thing is pretty big. This is a 16-bit multiplier now, using a fractal design. And I can show you. Okay, so for anybody who's new, this is what I've been working on. I'm going to be building Mandelbrot. Now, to get Mandelbrot to work, I need to use the least amount of relays so that the world can clock as fast as possible. So I need my multiplier to be, even if it's big, my multiplier needs to use less relays than other multiplier designs. And so to do that, I went and switched to something called a Vedic multiplier. And also in my a Mandelbrot generator, when I need to take the when I have to square a value, instead of using a multiplier, which is big, I will have a squaring unit which would be smaller compared to the same size squaring multiplier. Like, it'll have less components inside, so therefore I'll be able to have more of these total, so more parallelism. That's the goal. So you can see, well, here is a 2-bit Vedic multiplier. 2-bit times 2-bit produces a 4-bit result. Then you can see this 4-bit one uses 4 of the 2-bit ones, adds them together, generates an 8-bit value. The 8-bit one uses 4 of the 4-bit ones. The 16-bit one uses 4 of the 8-bit ones. So you can see how it scales. And I need each stage like that, I need separate for the squaring modules, because I need a separate size Vedic module per one, because the squaring units grow in the same way that these Vedic modules do, because they're based off of it, because the math that they use is similar. And the squaring module, Red Command is the person who is like hounding me that you can do a squaring module without needing to just tie 2 multiplier inputs together, and he's absolutely right. Yeah, it's physically big, but it uses less components. It's just my layout's pretty bad. Like, if you look at my 16-bit multiplier video, that multiplier is actually like smaller in size, but uses more components still. Because those adders are just bigger. Yeah. Yep. Also, I learned that like these insta-carry adders, you can pipeline them at 1 tick, except I ran into a bug where the XOR gate that's built into the game bugs at 1 tick for some reason, and so it doesn't quite work. So we're still limited to 2 ticks right now until Jimmy works out that bug, but I just reported that to him because I just found it like 30 minutes ago or an hour ago or whatever. Yeah, and yeah, for each Mandelbrot, I will show you. File, open recent. So for each Mandelbrot, I need I need 2 squaring units. All right, wait, no, I need. What do I even need multipliers for? Okay, I need a multiplier here I need 1 multiplier here for the A times B. I need 4 squaring units there and there. So 4 squaring units and 1 multiplier. So that's why it was so important to get the squaring units to be smaller, or like use less components than a multiplier, because if most of it is squaring units, instead of using multipliers that have the same input like I'm doing here, I will use a squaring unit that you just have 1 input that just gets you the squared output. and then I'll just apply my fixed point to it. And then so what I need to do is hopefully I'll be able to have 15 of these stages together, like chained together. So that's 4 16-bit squares and 1 16-bit multiplier. I need 15 of those in total, where the outputs go to the inputs of the next, chained like this. So here is what I mean. So inside each one of these circuits is this, which I was talking about. So we need 15 of those to at least get a clean render, because you can see like if I run this, that gives us a good render. Now if I gave it more iterations, like if I did 32, then instead of 15 grayscale levels, we'll have 32 grayscale levels. And you'll get like a little bit better looking image. So the more iterations you do, the better the color, the better the grade of the color you can get between. Well, yeah, that's why, like, well, I mean, in digital here, it's meant to be, like, ran on an FPGA. So my end goal here is really just, like, dicking around right now, just fucking around with different logic and understanding it. And then, getting this all to run on an FPGA. I mean, if I show you my browser right now, my browser is just filled with, like, I'm just trying to fucking, do I even have anything pulled up? No, it's just me learning how different, how I can implement logic more efficiently. Shit, yeah, I don't have any of the other shit that I was looking up. So yeah, it was basically, I want to have my FPGA drive an LCD screen that's hooked up through the VGA port that has a resolution of like 600 by 800 or whatever it is. I'll buy a screen. I need to then code my FPGA to then load from a block RAM and display the image from block RAM. Then I need to code the FPGA to generate the image in block RAM as from the, like, render the Mandelbrot and throw it into the block RAM. And then what I need is the zoom and pan on the Mandelbrot render, and then the color definitions. And then I'll have a zoom and pan, and then what I want to do is then massively parallelize it. But I think I should, like, just limit myself to 32-bit fixed point and like I don't know, like 480 by like, or 300 by like 240 or whatever, like that smallest resolution that you can go is like 360p, something like that, and buy a small 360p screen, and then write like my own FPGA VGA interface that can display on that small of a screen. But anyway, back to this. Yeah, so now I have, oh, see, I definitely like hardware a lot more than software, because I want speed. I don't want, like, when you're doing Mandelbrot, you're not, like, software rendering Mandelbrot, gross. Hardware rendering Mandelbrot, sexy. Like, I think anybody can sit down and, like, code something in C to, you know, or like, code something in Python or Java to render Mandelbrot. But to actually be able to build the circuits to do it, totally different. Yeah, like, the other thing is, like, when you're coding it, you don't have to worry about where your decimal point is. You don't have to worry about, like, your sign. All that shit is kind of, like, abstracted away for you, like you said, yeah. When I'm doing this, I need to know how many bits I have for my decimal, like, above my decimal point, how many bits below. Like, when I multiply, then all those bits double, and I need to get back to the original size somehow. So you need to know how to handle all that kind of shit. It's easy, but, like, that's called fixed point, or you can do it as floating point or whatever. Yeah. Yeah, if you don't want to have to wait till logic code comes out, you can always fuck around in Minecraft still. Yeah, assembly is interesting. I prefer designing my own CPUs and then writing my own assembly and designing my own assembly. Pink, it depends on what assembly you're talking about, because it definitely is. Like, my job threw me a problem. They were like, here's 4,000 lines of assembly that was written in 1996, you know, the same year you were born, Alex. We need you to figure out what it does and, like, fix it for our new LCD driver. And, like, to understand, like, everything going on, all the UART, all the, like, previous interfaces that were just, like, not commented in the code, it's impossible. So, like, assembly, yeah, I couldn't do it. Yeah, I mean, when you learn assembly in school, it's nothing like when you do assembly in real life. I mean, I learned assembly in school too, but then, like, what they teach you in school isn't, like, what you need to know for what you do in real life. Like, you don't know how interrupt vectors and all that shit are actually handled. You literally learn, like, the basics of, like, load this register, store this register, add this register, and it's, like, probably, like, HCS 12 or something like that. Like, once you start having to deal with interrupts and, like, memory maps and shit like that, it's just so much shit to deal with. Expressive code, yeah, and assembly. You see, this register just gets added. Right, but that doesn't tell me what this register is being used for, why it's being added. You don't know what if you're in the middle of a loop and, like, they're just accounting for it there. So now I have a 24-bit adder. I need to take the 16 bits out of this and put them onto the bottom 16 bits of that. So what the fuck? I'm pressing control. You're not wrong, the language, yeah. Fuck. Of course I align one off and then it fucks everything. Nice, there's 4 bits left over. Although shouldn't there be 8 bits left over? It's a 24-bit. 16. There we go. That's our 24-bit adder. Yeah, I mean, assembly is super fun because it gives you like some understanding of like what's going on under the hood. It has to give you like you have to be like one step closer to the underlying hardware. Fuck, I keep fucking this up. One, two, three, 4, 5, 6, 7, 8. Oh, peace out, Codelta. Wow. So we have our 24-bit adder there. And now, I think we're going to take our 24-bit adder, rotate it, my GitHub or their GitHub? Oh, each adder output. One of these is misaligned there. Okay, those are all aligned. There we go. This results here. Oh, fuck. I need to shift that up. I need to get 8 bits, so 16. But I'm going to go higher than 16, so I'm going to go 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8. Alright. So now we need 1, 2, 3, 4, 5, 6, 7, 8. Delayer, short delayer like that. So we need so yeah, what we're actually going to do is there we go. Okay. There we go. 16-bit result. Synced. Let's see how this works. This is gonna be a bitch to hook up. Alright, we're almost there. One more. Alright. That should be FE01 when it comes through. I have it set for 1 tick per second right now. So there we go, FE01. It didn't fuck anything up. Now, if we do this all the bits, it should be like 4 Fs in a row, then E0001. Or like a few zeros and then a 1. It would be similar. I think that's like correct. Split it up based on can you turn on the game music options, audio, music? There we go. I'll let you know when it starts playing. If you can't hear it, I'll turn it up. One, two, three, four, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. Nice, so we have FFFE0001. They do. The relay blocks do make relay clicks if the sound is on. Options. Master. Here, I'll grab a relay. So this, unless, I don't know if that's the switch making, oh, maybe that's the switch making the noise. Yeah, never mind. I'm just surprised that fucking multiplier is working like that easily. So now to render out a screenshot in game. 2. Yeah. Hey Jimmy, thanks for joining. Yeah, it probably would get annoying. I would definitely not have it like, if it was a setting, I wouldn't have it enabled. Anyway, Jimmy, thanks for joining. If you see here, I have a 16-bit multiplier that's unlike the other 16-bit multiplier that I made that you liked. So you can use this in your example or video or whatever if you need to. But this has 16-bit inputs. 1, 2, 3, 4, 5, 6, 7, 8. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, 16-bit inputs. And it makes a 32-bit result. Oh no, this is like 24 or something? I don't know. I'm actually not sure how that didn't... Eight, 16, 24, plus another 8, that's 32. Yeah, okay, 32 bits on the output. Yeah, it being spread out wasn't like a... Oh shit, I did not mean to change the music or switch to the main menu. I meant to lower the volume of the music a little bit. I hope it still plays. Shoot. Alright, options, audio. I just wanted to lower it from 15 to 5 because it was pretty loud at 15. Yeah, Jimmy, this wasn't like, my goal wasn't to make it so spread out. It's just, it's a fractal in nature. If you're looking, here's a 2-bit version, a 2-bit Vedic multiplier, VEDIC. It's not a Wallace tree multiplier, it's Vedic. So here's a 3-bit one, and it uses half adders only, no full adders. Then what you do is you take 4 of those. You have 1, 2, 3, 4. You add some logic adders, and then you have a 4-bit one. You take 4 of these, here, 1, 2, 3, 4, and each one of these has 4 2-bit ones on it, and you get your 8-bit one. Then you take 4 of the 8-bit ones, 1, 2, 3, 4, and you get your 16-bit one. So it's just like a artifact of how they get stacked, and because of the way they're stacked, like this, I couldn't make this any smaller, so it just becomes what it is. But they should improve performance for my multiplier in general. Hey, what up? How's it going, Josh? We're live right now. I can't hear you if you're talking, by the way. Yeah, so now yeah, and the other thing I have is squaring circuits don't need to be as big as that multiplier, or don't need to be don't need to use a whole multiplier. They're going to use those Vedic multipliers, but they don't have to be as slow as a whole multiplier. It's going to be interesting. Like here's an example of here's a 4-bit squaring unit. Oh, and this is what I wanted to point out. Okay, I'm glad you're here. All right, Jimmy. So I'm going to show you a bug. So this will get stuck on for some reason. Yeah, the game's just not... Wait, none at all? None of the clicks or anything? The desktop audio is enabled. Settings. Maybe it's just very quiet. I have to boost my other audio. Maybe I have to boost that one as well. Let me know if that's like overwhelming and you guys are like screaming, and then I have to change it back. But I hope you can hear that. anyway, I'm running at the game at 1 tick per second right now, and to show you that this thing works in general, here is the number 6 on the input. A few ticks later on the output, we get the results. Wait, did it update? I'm confused. Oh, okay. Yeah, okay, yeah, that is the result. Yeah, so 6 squared is 36. So that's 32 plus 4 is 36. So I'm just showing you that it works. But when I stream in 1 tick numbers, so what I'll do is I'll press this button for 1 tick, it'll make it through, it'll encode the number 1, come through 1 tick, encode the number 2, come through 1 tick, 3, so it'll just count up 0 through 15. Every tick it'll update these inputs, and it'll stream through this. So, oh fuck, I'm running out, what is my, oh, because I reloaded, fuck, wait, hold on, I have this. There it is. Alright. Alright, so it makes it through, so 1, 2, 3, 4, 5. So you're going to see that it's going to go 1, 4, 9, 20, 16, 25. That's where, no, it was good there, but then fucked up there. It showed like 25, I don't know, 49. Wait, did it do it right that time? F2, F1, Control F2. Did that work that time? What the fuck? 1 squared is 1, 2 squared is 4, 3 squared is 9, 9 squared, 4 squared is 16. Then we have 25, which is 5 squared. Then 32 plus 4 is 36, which is 6 squared. Yeah, that's fucked up. Wait, or not. Wait, oh, that's not 32, that's why. 4, 8, 16, 32 would be that one right there, because we have 32 plus 8. Wait, what? Yeah, this is... Yeah. And I don't even know where 225 is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that's 225 there. Fuck, man. I'm confused. What is this? 8 times 8 is 64. That looks right. I just don't get how this can be bigger than that. Like, how does that... That's wrong. Like, and I think the reason... Yeah, watch this. So I'll show you how I got this to break visibly. Alright, there we go. Alright, Jimmy. Watch this. Now we'll do the same thing. And we're gonna watch this XOR. That XOR just refused the output, and then it comes through like way late. It was just outputting stuff that it didn't have, like, and now it's stuck on. So Jimmy, if you're watching that, that's the bug that I'm having with this. When I try to stream data through it too quick, shit just gets bugged. Well, this is the small isolated circuit. Fuck, where did I go? This is the circuit. This is the test circuit here. To show you, like, here's the circuit without the test stuff on it. This test circuit is to show you what's coming through. So basically you have screens that show you the bit of each bit. I guess I should have separated by 1 so you could see them better. But the screens show you each bit, and then there's 1 ticket delay. And so you just chain these modules together to show you like 1 ticket delay chain. So you can see if it changes in 1 tick or if it changes in 2 ticks, you know, then between transitions 2 will be the same state or something like that. So this was checking the timing. And so like all you'd have to do is press play or press that button for a tick and you will generate this error. I just don't know how to save this. How do I save my boards? And it's like, I guess I could do like 2 ticks stream, but like that sucks. That's the same speed as Minecraft then. How do I clone this board? Yeah, I'm not sure how to, I forgot how to clone the board. Using edit board menu, how do I do that? X. Save board. 1 tick. Square. 1 tick. 4-bit square name. Alright, so now I have that board, so I will post it in the Discord. Where do I find that board is the question. My Steam properties, local files, browse local files, save boards. Yeah, okay, I'm assuming I will export that. There we go, Jimmy. There's the board file. I hope that works for you. I hope I did it right. Yeah, so all you have to do is press, like, well, what I did to make sure that this was only pressed for 1 tick is I lowered the game speed that I'm at to 1 tick per second so I could actually just verify that. And then I could see the stream through. Otherwise I would need to latch all this. Didn't want to latch it. So instead I just take a screenshot after 15 have flown through. I think I put enough on here to see all 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, I put 16 on here so you can see all 15 and 1. Yeah, here's a 2-bit square if you wanted to see how this was done. It's pretty cool. We'll go back to like a game speed that isn't miserable. So yeah, 0 times 0 is 0, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. So this is the heart of it. And that you could see is then used twice. It's used here and here. And then we have a 2-bit Vedic mult. So then to scale this up, we're going to take a copy of this, one on top of the other, with a 4-bit Vedic mult to the side, and then do the addition that we need. Then 2 of those newer ones with a larger multiplier, and then yada yada yada. We'll just keep scaling up, and that reduces the amount of multipliers needed inside the squaring. Because Vedic mults are built recursively. It's like that's the beauty of doing it like that. So I guess that's what the step I'm on right now actually is to stop being a lazy fuck and actually get it done. So if I Control G, We'll do this over here. So I have that. And now I'm going to need to like I don't understand the movement on the board, but if I can get it to where I need to, massage it where I need. That's good enough to be in the same spot as the one below it. Now I need my 4-bit. I need this guy. It's handling the amount of shit I'm pasting in pretty well. Alright, here's going to be this, the 8-bit square, I believe. It's using 4-bit shit. So now if I come here, alright, we need to find the square now. Okay. Let's do it. So now I have my squares. I think I just... Okay, so I need to get an 8-bit input. Let's do that just so I don't get confused first. Alright, so we have our 8-bit input. So now the bottom 2 bits or the bottom 4 bits will go into the bottom 4-bit square. I don't know why I'm not doing that. Bottom 4 bits go into that. Top 4 bits will go into the top there. Also, Jimmy, your ambient occlusion is fucking with me. I'm gonna turn it off. Do you see how those pegs are turning colors that they shouldn't be? Options, video settings. Or maybe that's the bloom, I don't know. There we go. Okay. And then now we're gonna say the bottom 4 bits go into one input of the multiplier and the other go into the other. Okay. Come on. Please, 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 yes, okay. Fucking beautiful. When it works, it's nice. Okay. So now the multiplier produces a 8-bit result, and we're gonna shift that result left, aka up, by inserting a 0 here. I don't even know why I'm doing it like this. This is a dumb way to do it, but there we go. Insert a 0. So we left shift it. It now becomes 8 bits. Goes to 9 bits. We have a 9-bit number, and we're going to okay, so I need the bottom 4 bits off that. I need the bottom 4 bits off the first square here. I'm just going to do this. Cool. Okay, so we took our 4 bits off. Now the next 4 bits have to come and be added. So I need a 9-bit adder. 1, 2, 3, 4, 5, 6, 7, 8. Okay. There's our 9-bit adder. So we need that 9-bit adder to line here. There we go. Scroll back a bit. Alright. So we take that left shifter and we hook that up 0th bit there, going to the 0th bit here. Motherfucker, I have to alright. I thought this version had this, but it didn't. 1, 2, 3, 4, 5, 6. left shifting. So fucking easy. Alright, so there's one input to that. Now the other input is just the top 4 bits of this being the bottom 4 bits. So we just have to go 1, 2, 3, 4, 1, 2, 3, 4. Okay. Now, out of that ripple carry-outer, or out of that, well, it's synchronous because we're using an insta carry-outer. So we're going to take the 4 bits, we're going to take the bottom 4 bits out of that and place them here. One, two, so then the top, wait a second, take 4 bits out. What did I do here? So I have my square. It is, but he updated the. It has to go on Windows, but he updated the beta build. It does say beta on the, I believe in the title and in the thumbnail. Excuse me. So what am I stuck on right now? Alright, out of the left shifter, alright, so out of the multiplier it gets left shifted and then gets added. So out of the multiplier, it gets left shifted and then gets added. The other input just holds 0, and the output of that oh, we just take the top bits that exist. So out of that ripple carry-outer, we're just going to take the rest. So we took out our 4. So it's a 9-bit ripple carry-outer. We took off our 4. That means 5 bits are going to come out. But we really have 8. So this needs to be an 8-bit. we need the top 5 bits out of that. Going to the bottom 5 bits inputs here. I know why that happened, just misaligned here. Okay, so now we have that going into there, and now we need the 2-bit square. The other input. It's going to be a 4-bit square. It's going to have 8 bits. So these 8 bits then need to make its way over to there. Damn, that's going to be a bitch and a half. What if I... Can I bring this... Let's see if this will work. Also, Jim, if you're still watching this, when you pick up a board, it rotates it 180 degrees for some reason. Like, automatically on its own. Oh, that's a nice curve. That's what she said. That's what he said. Alright. Thinking this is going to be a cunt. I'm not looking forward to that. Moment of truth here, boys. Please, please be 225. Okay. I should probably like finish the busing, huh? Just turned on, the music just stopped actually. Oh, wait. Options. audio. Yeah, it just gets hard to like play with the music on too loud. I'm not one of those people who can think and play with and have music on because like I'm not just. What the hell? No, I don't need to be invited to no Discord server. There we go. So. Least significant bits. Shit, I didn't think that actually would connect. There we go, there's 225, but now if I do this, it should be FE01. FE01. Very nice. Okay. That is so cool. So, instead of needing an 8-bit multiplier to square, we only need 4-bit multipliers. You literally need half. So, like, here's my 8. Okay, so here's, if this puts it into perspective. Alright, for anybody watching. Here's an 8-bit multiplier that I built. If I want to do 8 squared, or if I want to do, you know, a squared, or both of these were a, and I just tie these together, using a multiplier, this is how big it would be. Using a circuit specific to just squaring, it's this. So that versus all of that. It's like literally a fourth. Or a half, maybe a third. I think that's insane. Now what we're going to do is use 2 of these, and then an 8-bit square, and we'll have a 16-bit squaring machine. And then once we have a 16-bit squaring machine and our 16-bit multipliers, we build Breslin hams. So imagine those 15 of them stacked long, 15 stages, along with 4 of these per stage. So 4 of those per stage stacked like this, and then 15 stages long, hooked up to a screen. It's going to be beautiful. And I'm gonna try to get away with using a 4-color screen, because then we can render Mandelbrot in 16 grayscale, like in 16 shades of grayscale. Imagine that. But yeah, for now, guys, I think I'm gonna stop because my neck is starting to hurt. And I've been streaming for pretty much all day, so I thank you for joining me. I hope you got to learn something new and see like some new architectures for stuff. This scoring circuit is going to be insane, and I hope you guys stick around for the ride of generating Mandelbrot inside of a video game. Because we're doing the hard part first. We're going to get all the math stuff done, because all we need is squaring and multiplying for now. And then we'll build an absolute value machine, which is going to be like literally the easiest. Then we have some counters to build. And then we have to build the screen, some decoders, and we're done. So yeah, I think that actually one of the harder parts will be the screen, getting that to stack how we want. But I'm confident we'll get it. Anyway, I'm signing off. I'll see you guys next time. Please like and subscribe. And yeah. Peace out. if I could figure out how to shut down stream. There we go. See ya.